Hello. Hello. I would like to discuss a knapsack problem, which is problem J, sorry, from ACM ICPC World Finals 2011. The kinda bizarre moment is that we didn't solve this problem during the contest, and this is embarrassing because this problem is actually really easy. So it was solved by more than 100 comments or teams during the virtual participation. So you can see it here. 758 attempts and over 100 accepted for problem G. But we didn't solve it in 9 tries. I guess we had incorrect approach for this problem. So what is this problem? Let's start with reading the statement, of course. So we have a pyramid, and there is a notion of a high pyramid and a low pyramid. What is a high pyramid? So we start with some foundation, which is square. For example, 10 times 10. On top of that, we put a 9 times 9 square. We continue it one by one until we get a 1 by 1 square, which is a pinnacle. So this is called the high pyramid. And the high pyramid can be created for any basis except 1. So you cannot have a pyramid of height 1. It should be at least height 2. So you can choose, for example, a pyramid consisting of 5 cubes, which is 2 by 2 in the foundation, and on top of that is 1 by 1. But you cannot have a single 1 by 1. Also note that high pyramid always ends with 1 by 1 square. It cannot stop in the middle. Also, there is a low pyramid, and it actually does the same, but in it we jump by 2. So if we start, for example, from 10 by 10 square, then we jump to 8 by 8 square and 6 by 6. So all numbers no more than the side of the base of the same parity with the base. So in this case, low pyramid can end either with 2 by 2 square or with 1 by 1 square, depending on the parity of the base square length, or side length. And again, you cannot just take a 2 by 2 square or 1 by 1 square. These are incorrect pyramids. They are not pyramids in this problem. After that, we have a furrow. Is it pronounced furrow? Furrow. I don't know. Let's call him Egyptian king. So the Egyptian king has a lot of stone cubes, and we need to build several pyramids from these cubes, one or more. We cannot leave a single one unused. And the restrictions are here, so we need to find the minimum. We need to spend all our cubes to build one or more pyramids, but the minimum possible number of pyramids. Also, all pyramids should be different. The height should be at least 2, as I said. And also, if we enumerate them from the biggest to the smallest, then the answer should be lexicographically maximal. So the largest of the pyramids should be the largest possible, the second largest after that should be the second largest possible, just largest possible. The second largest pyramid should be largest possible conditional that the maximum pyramid is already chosen, and so on. And we need to find this solution. Yeah. Okay. Let's try and approach this problem. So, first of all, I think we will discuss this problem, and at the same time, we will try and implement it on C++. So first of all, we will need a function which calculates the height of a low pyramid and a high pyramid. Actually, you can avoid calculating the formulae, but I think it will be more useful to calculate these formulas, to infer them. So, high pyramid. Pyramid. What is it? So, actually, it is 1 squared, then 2 squared, then 3 squared, plus etc. plus n squared. This is the volume of this pyramid, so the number of blocks, of cubic blocks. This formula is known, I would say. So it is n times n plus 1 times 2n plus 1 over 6. So this is the basic formula which I will be using later. So this is easy. What about low pyramid? And there are two kinds of pyramids, with an even base and with an odd base. Let's start with an even base. So n equals 2k. In this case, everything is the same, but we start with 2 squared plus 4 squared plus etc. plus n squared. You can notice that all these numbers are even. Moreover, they are divisible by 4. So let's put it here. And look what is inside the parentheses after division. So now we have just ordinary squares. And we end with k squared. But this is already known, yeah, because this is simply 2 squared times k plus 1, 2k plus 1 over 6. Okay, to continue this, let's actually replace k with n halved. So we have n halved times n halved plus 1 times 2 times n halved plus 1 over 6. And if we substitute this, we get, okay, this 2 squared just goes here and destroys these 2, and it destroys these 2. So we end with n times n plus 1 times n plus 2 over 6. This is for the even n. Now let's go with odd n. N equals 2k plus 1. Let's see. Or minus 1. Even minus 1 is better, I guess. So let's see what we have. We have 1 squared plus 3 squared plus 5 squared plus etc. plus 2 plus n squared. What is it? Let's notice that all even numbers are skipped here. Let's add them. So these numbers are 2 squared plus 4 squared plus 6 squared and finally n plus 1 squared. Okay? But then you might also notice that it is the sum of all squares till n plus 1 squared. minus only the even ones. And we already have formulae for both of them. So the first thing is n times n plus 1 times 2n plus 1 over 6. But since we have n plus 1 here, it goes as n plus 1, n plus 2, and 2n plus 3 over 6. Then we subtract this thing. Okay, you don't see my mouse pointer, so I will draw an oval. This thing, we need to subtract it, and again for n plus 1. So n plus 1 times n plus 2 times n plus 3 over 6. Let's subtract it, and you can notice the common it's called multiplicand. Oh, multiplicand. Maybe yes. So let's group it. So in the parentheses we have 2n plus 3 and minus n plus 3. So this is just n. And we end up with n times n plus 1 times n plus 2 over 6. So funny enough, this is the same formula as here. So this is equal to this one. Yeah. So we can start with these two formulae. Okay, int phi pyramid. And we return base side times base side plus 1 times 2 times base side plus 1 over 6. Yeah. And for the low pyramid, we need something similar, but some other formula. So low pyramid so it is base side times base side plus 1 times base side plus 2 over 6. You can notice that not only this is a lower pyramid, it also has a smaller volume. Yeah, it's actually obvious, but you can see that it is asymptotically smaller. Yeah, so the major component here is base side cubed. Yeah, because it is like going to infinity, and we have a polynomial of base side. So we're looking at the leading term of this polynomial, which is base side cubed. And see, this is multiplied by 2 and then divided by 6. So this is 1/3 of base side cubed. But here we have base side cubed over 6. So asymptotically, lower pyramid is 2 times smaller than the high pyramid, which is also kinda intuitively easy because you see here we just removed half of the layers, and the layers are evenly distributed, even and odd. So they should be kind of the same. But I really think it's notable that the formula is same for odd and even n. Usually it is not. Yeah, for example, you can express. So if maybe you know that n factorial is actually I hope I'm not mistaken, but I think it is gamma of n plus 1 or minus 1. I'm not sure. So in terms of gamma, n double factorial is different depending on the parity of n. So if n is even, this is simply 2 to the nth times n half factorial, and we get this nice formula with one gamma function. But if n is odd, then this is a bit gross. There are two gamma functions in this representation. So, for example, in this case, even and odd cases are vastly different. What to do next? Okay, we have the formula. Actually, you do not need this formula because, again, as you see, base side cubed over 6, this is kind of fast growing function. So for base side equals 200, for example, this is already more than million. Yeah, it is more than million. So you will not need any sides which are greater than 200. Yeah, and so actually you can do it in linear time. You can just add them up one by one. You can make an array which is called low pyramids, in which you store the volumes of these pyramids. And when you look at the point I, you say that volume of I is volume of I minus 2 plus I times I. And in the cycle. And for high pyramids, it is even easier because you just use -1 here. And also you need base case for V0 and V1, for example, which is 0 and which is 1. Nice. So now the hard part, how to solve this problem. And there is a way which is called a knapsack. So it is an exponential method, but sometimes we are okay with exponential methods if the number, which is the exponent, is not very high. And so it is exponential in terms of the size of the input. Yeah, for example, if you have this number c, this is like 6 digits long, but the time that you spend is not proportional to 6 or some polynomial to 6. It will be proportional to 10 to the 6. Yeah, so it is exponential of the size of the input. But if we consider c, for example, in a unary system, or we just allow c in the asymptotics, then this method is linear in C, of course. So knapsack method just says, let's store something for each size. Yeah, so not only we will know if it is possible to make a pyramid of size C, we will know it for each size below C. And each next of them will be computable depending on the previous ones. What would we like to know? I guess we would like to know. So in the basic case, we just would like to know if it is possible to represent this sum. So I will write something which is actually not really correct. Oh, my camera is so friendly. Never lets me down. I will use files in my problem with an ifdef pragma. So on PC, reopen input.txt. It is just for using the files because I like them more than the console. Output w out, and as you see, Visual Studio is angry, and there are several reasons. First of them is I did not include iostream. Second of them is I should have used namespace std. And after that, it will also be angry. It will not compile. It will say, citing, this function or variable may be unsafe. So to prevent this, I usually just write here define crt secure no warnings by heart. And now it works. And also, just in case, I have 2 lines for speeding this up. IO sync with stdio false and scene.tie null ptr. Okay. And here we just ask this thing. Okay. What I will be doing is automatic multitest. So I will say solve tests. And this function will just, while true, solve test. Actually, not while true, but while solve test. So solve test will be a Boolean function which returns true if it were able to read the number from the input. So we read n, we read c. And if it failed while reading c, which can be checked like this, we just return false. Otherwise, we will need to return true, but before that, we need to print the answer. So now I print the answer. No, I will. We need to decide what is the format of the answer. Because here we have some vector of sizes. Yes, so I will just return the vector of sizes. It does not know what is a vector, which we will fix immediately. And it also doesn't know what is findAns, which we will fix later. So findAns will return the list of the sizes of the pyramids. Actually, no. So as you see here, each pyramid is denoted by the size of its base and its type, which is high or low. So I would like to do the same, and for that the answer will be actually vector of pairs of integer and boolean. So integer is the side length of the base, and boolean is whether it's high or low. So true for high and false for low. Let's for now just make a dummy function which doesn't do anything nice. And here we just return nothing. Here we will iterate through the ans, but first we need to check if ans is empty. If it is empty, we print impossible. No. I also forgot that actually I need multiple tests here because so it is not like what I could do or could not do. This is mandatory in this problem to have multi-tests in several cases. And also, the end of the input is not denoted by last integer. It's denoted by additional 0 on which you do not need to reply. Yeah, so there is no case 3 here, although there is a 0 here. So we not only we need to stop when we didn't read an integer, we also need to stop if we see that c is 0, is equal to 0. We also return false here. So if ans we actually always print case something, and we need here the test number. So we'll put this in the arguments. And here we will put the number of the test, but since it is not known, we will initialize it with 0. Great. Let's continue. Then I need to print a space, which I can do here. And now I need to print either impossible or I will do it with the line break. Or I need to print all the sizes. So I will use for int I equals 0, I equals less than the answered size plus plus I print ans ith dot first, and then I print ans ith dot second, and if it is second, so if it is true, then I need a high, otherwise I need a low. Actually, there is something crazy, which is written like this. Yeah, so if ans I dot second is true, then I go into this element, and otherwise I go into this element. And then I either need a space or a line break. And for that I will use the same trick. So I need only a line break if I plus 1 equals ans dot size. Crazy, but this is C++. What would you do? Okay, now we need to find the answer. Sorry for so much time, but now I'm coming to this actually incorrect solution. So we will store for each size of the pyramid. Whether it is possible or not to get it. And I will need it till C+1, I think. Okay, now we need all sizes of all possible pyramids. And we will store them in a vector. So I actually want a structure for this. Struct pyramid. And it has its size. It has its type. Okay, let's go. For int I equals 2 plus plus I. So let's try a pyramid. P dot base equals I and okay, just first equals I, p dot base dot second equals true because this will be a high pyramid, and p dot size equals high pyramid of I. And if p dot size is greater than c, then we will break, else we will push this into the pyramids. Okay, the same goes for the odd pyramid. Oh, I meant low pyramid. Great. And now we will iterate over all pyramids and over all numbers. Yeah, so let's go. For int I... first of all, we need to sort the pyramids. I want to go from the smallest to the biggest one. For that, I will just use sort. And sort is in include algorithm. So we iterate through the pyramids. Okay. Also, I want to start with something impossible. So let's use -1, which means that I cannot get this state. So let's go through all numbers. And I want to check whether I can get now this number. So I want to check whether this number was inaccessible. So vi dot first was -1. And I can use the current pyramid, which means that I is at least pyramid dot size. And if this is the case, I can say that vi equals p dot base. Actually, just pyramid dot base. That's it. Great. And this is the whole knapsack, I guess. So in the end, we just return. We need to restore the answer. For that, we look at vector pair int bool ans. We will return the answer, but previously we will look. So int current volume will see while current volume, okay, greater than 0, and while v dot v current volume dot second dot first is not -1, we do the following. We add this pyramid to the answer. Yeah. Then we subtract it from the current volume. We can do it like this. So if v current volume dot second, then this is a high pyramid. Otherwise, we need to subtract low pyramid. But I don't like this way, because this is not how programming works. You better create a useful function. Do we see that we need some useful function here? Yes, we would like, based on this boolean, find the volume of the pyramid without any ifs. For that, we would like to create a new function, which is called, for example, size of pyramid. It takes two things. Actually, you can just take the base. where int bool base. And depending on the base.second, it will return either high pyramid or the low pyramid. This is much better, because this is a function which you can use afterwards. So now we just have only one line instead of these four, just current volume minus equals size of pyramid of v current volume. Great. And return answer. So this is totally incorrect solution, although everything seems right. And to understand that, we need to run it on some cases. I will just create several easy cases. Something is wrong. Yeah. See, you have so many errors and they all do not make any sense. Some fails to specialize function template. There are two ways to understand it. One way is to be experienced and know that this is because your class pyramid does not have a comparator, and it needs because of the sort. But we will go the second way, and we just build it again and look into the build messages. Yeah, so you see error operator surrogate func, no matching overload function found. Now what we need is to keep track of these messages and see when they point into your code, because at some moment they will point into your code. So this is still not your code, and this is not your code, and this is not your code. Oh, this is your code. So you see that something is wrong with the sort. And to fix it, you just need to add a function which is called comparator. It allows you to compare two pyramids. And say if our current pyramid is less than the other. We will just compare sizes because this is how our sort should work. Okay, now it should compile. Yeah. So this is definitely fine, but this is something not nice. You see, it for some reason it says that everything starting with 4 is 2L, which is not true. We should ask ourselves, why did this error came here? This is because when we was... So, first of all, 2L is definitely a... it should not be allowed, actually. But let's forget about that it shouldn't be allowed. So let's assume that it is allowed to have this pyramid of 4 squares, of 4 cubes. So what's wrong? For some reason, for 5, it is also saying that you can cover 5 with just these 4 squares. What do we do in our solution? We look at 5 and we say that we can get from 5 to 1 by eliminating 4 squares. What we didn't check is that actually 1 is reachable, which is not nice, because 1 should be reachable in order to for 5 to be reachable. If 1 is reachable, then 5 is reachable. But if 1 is not reachable, then if we want to get 5, we need some other way. This way is closed for us. To do that, we can simply say that int... So if int is -1, then the answer is impossible. We need to fix it for 0, because 0 is actually possible. You can take no pyramids, and this is a correct way of making 0. So we say that v0 dot first is 0. And then we need to check here that the smaller number is accessible. So vi minus pyramid dot size is not -1. In this case, we can do it. Oh, here I guess it should be just pyramid size without braces. So let's run it again. Okay, now it's better. Also, let's fix immediately this problem. Yeah, because 2L is not an allowed pyramid. Yeah, because this is of height 1. But this is kind of easy to fix. We just start the low pyramids from 3. So this is low pyramid. We started from 3. Okay, now this is impossible. But we have another problem, which is 2H to H. Normally it wouldn't be a problem. But here we have this condition that okay, you have condition, I guess it is here, that all pyramids should be different. Okay, you cannot use the same pyramid several times. To approach this, there are several ways. What I like the most is choosing the right order. So what is the problem? The problem is you have some number 0, 5, and 10, for example, here. And you say, since 0 is accessible, we also can access 5 with this pyramid. Tun, 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 tun. 4 and 1. But since now 10 is accessible, can access 5 through the same pyramid, we can also say that 10 is now accessible. This is a problem because now we have a path of 2 pyramids of same type. How could we fix it? Actually, we can just go from the right end to the left end. If we went from the right end to the left end, it wouldn't be possible. Yeah? So assume that you have a path in which there are 2 edges of this type. Yeah? But notice that when this edge was created, when this edge was created, this edge didn't exist. Yeah, if they are of the same type, the right edge was created before the left edge, so the left edge didn't exist. So actually, this vertex should have been accessible with some other approach, without this pyramid. So if we go from the right to left, we can approach this problem of duplicates. So let's do it. It's not really hard. We start with C. We go to till 0 and we subtract 1 from I. Let's look now what we have. Now it's fixed, yeah? See, 3L. 3L is pyramid which looks like this. It's first of all, this is 1 cube, and now there are 3 cubes. And the same here. Great. So this is 3L. No, 3L. Which is of size 10. But still, this solution is wrong. Sadly enough, this solution is wrong, and I guess we will get it if we run it on the sample, which is 28 and 29. Let's try and do it. it says 3H, 3L, 2H. Also, actually, the other thing that it does, it lists all the pyramids in decreasing order, yeah, because in our solution, we list them in increasing order. And this means that if some vertex is accessible, first of all, we jump with the biggest pyramid, because it was the last pyramid in this chain. Yeah? If it wasn't the last pyramid in this chain, then this chain would not exist by that moment. Yeah, for example, assume that you have, for example, pyramid of size 2, then of size 4, and then of size 3. This is the chain by which you get number 9. Then it wouldn't be possible, because when you add this chain, you also check that this vertex is accessible. But if there was this edge, yeah, notice that this edge is greater than 3, so it will be added later. So now, when we add edge 3, this does not exist. So now there is no chain, and so 6 is not accessible. So it will not be used in the knapsack. So this automatically gives us the decreasing order. Actually, if, for example, it is asked to make the increasing order, you could easily just iterate through the pyramids from the other direction. Great. Still, the solution is not correct. The reason is we do not look at the lengths of these representations. So we do not check that they are optimal. Maybe we will see it somewhere here. Let's try, maybe we'll see it. Maybe it's not easy to see. How can we see it? Okay, I will not find you the test, but still this solution is incorrect. I guess we could draw it, but I don't think it will be useful very much to spend your time on this. So we will just continue. So actually we would like to keep track of the sizes of the pyramids, or the numbers of the pyramids. So not only we would like to check if C is accessible, but also if we can get C through I don't know, X pyramids. Yeah, we would like to know if we can get C through X pyramids. Yeah, so we will combine our approach of going through C to 0 in decreasing order to avoid duplicates. But still, so if we are in some number I, what we would like to do We would like to check if we can, using X pyramids, get number I. Then we can, using our current pyramid, P, go to I minus P dot size and check if it is accessible via X minus 1 pyramids. And if so, then great. But also, if it is already possible in X, we still need to update the answer. We still need to update the answer because maybe we found some answer with little maximum, but then we need to increase this maximum. Okay. I know what I would like to do. Let's just call this function findAns version 1. And then we will compare this function with some future functions, which will be correct. And you will see that actually findAns is more optimal than findAns v1. Okay. I guess what we need now is to... Actually, I don't know. Maybe we can just keep track of minimum possible number of pyramids and how to access it. Yeah? Maybe this is the way. I think let's try it. Let's try it. So, sorry, Microsoft Word. For some reason it opened. And I don't want this. Okay. So now it gets huge. We want pair. So it starts to be annoying, so I would like to make a structure again. So now we need pair of int and bool, which is the optimal base which we need to choose. Also, minimum number of pyramids. And that's it. I guess that's it. So now we have this DP state. And I think we would like to make a constructor. Because sadly enough, there is no C++14 in the testing system, so we need to make anything as easy as possible. For the compiler, of course, not for me. So this DP states for number n says that we can get number n with this many pyramids if we start with this base. So here we need to make a DP state of this base and this number of pyramids, for example. No, I would like to make it as big as possible. So let's make it infinity, where infinity is 1e9, for example. So v0.first, not dot first now, but dot base dot first is 0, and v0 dot min pyramids dot first, not dot first, just min pyramids is 0. Great. So what do we fix in our solution? First of all, now, instead of checking that something is -1, we can just check that this number is big. So, let me think. Great. Okay, so we're checking if... We're not checking this for anymore, of course. I think we can just eliminate this check, and this will be better. Let's just eliminate this check, and you will see that the answer sometimes gets better. And this is not fixed for now. This is fine, this is fine. This will not work for now. Okay, I just destroyed this function. I want to show you that sometimes v1 is not correct. So let's just iterate through all numbers. Okay, I will need to print uns. And this function will just do this. And here I will print uns. Great. So the stress will do the following. It will check the answer of v1 and of v2. And if they are different, it will report. So it will say failed on I. Then it will print v1 ans. And it will print v2 ans. Okay, find ans v2 is here. Okay, and instead of solve test, I will show you that stress finds a test. No, it does not do it. Okay, it broke. It broke, or I don't know. Okay, maybe they're both correct. Hmm. I don't believe that. Sorry, but I don't believe that. So it checked that this is -1. No, I can't believe that. This is the same. No, this is not the same. Ah, it printed in here. Sorry, guys. Of course it stopped. Let's return from this function. Great. Okay, you see that the minimum test is 30. Yeah, so v1 ans says that we need a 4L and 3L, which are actually, it's funny. Yeah, so for high pyramid is 1 squared plus 2 squared plus 3 squared plus 4 squared. But v1 ans just expressed it as the odd sum plus the even sum. So only 2 and 4 here and 1 and 3 here. But of course, this is the optimal answer. So you already see that it is better that even if we already have the answer here, it is still better. It is still better to rewrite it because the new pyramid is actually smaller. It's still not always correct. So it is not always true that v2 is greater than v1. Possibly v1 would get a smaller answer with smaller number of pyramids, and v2 maximizes the size of the biggest pyramid, but it does it non-optimally because it increases the number of pyramids. So none of these two solutions is correct. What we need is to watch accurately what we are doing here. So we do not check, of course, that I is -1. We of course check that I is at least pyramid size. We also only need the replacement if our current answer is greater than this the answer in after the transit. Yeah, so if our current answer is greater than the answer if we remove this pyramid dot size, then we do it. So here I put pyramid dot base, I guess. No? Ah, I need a DP state. So I need a DP state which is base and min pyramids. Okay, I can do it. Base and new min pyramids, which is now this +1. So what do we do here? Actually, all the same. Base dot first dot base dot base. Let me think. I believe this now might be even a correct solution. Let's again stress it with v2 now. Let's stress it with v2. Okay, it found something. Failed on 50. Yeah, because v2 found a bigger answer, as I said, with bigger basic pyramid. 5 low. 5 low is 35, and 4 high is 14 plus 16. So it's 30. I guess it is 30. Yes, this is 30. This is 35. So at first glance, the biggest pyramid, the better. But actually, this is the worst answer because it has bigger number of pyramids. So is it always fine just to do it? I'm not sure. Let me think. We can always, since this is upsolving, we can just start with sending this into the system. Yeah, so let's start with it. Notice that some people, before sending to the system, they comment their input and output. I prefer not to do that, and instead I put these guards, if defs. So this thing actually kind of checks that this is on my PC, because on my PC, right here, it is checked, it is put that the preprocessor definition on PC. So the things knows that it runs here. And in this case, I run these two lines. But on the testing computer, there will be no on PC. And this will run fine without these two lines. So let's try and send problem G. It is okay if the solution is incorrect. I have an idea what could go wrong. And we will fix the solution if so. It can be compilation error, of course. We're just waiting for so long for compilation error. Time limit exceeded. Oh my. It's interesting. I didn't expect it. Ah, I get it. Actually, I didn't need to do this every time for each multitest. So this can be done only once. This, of course, can be done only once. Okay, to fix this, we need to create some solver. Which just does the dirty job. So pyramid solver gets number n, which is the maximum number, actually c. Let's take c. And we will have vector db state here, and it puts v into v c+1. Actually, now it goes like this here. Yeah. Okay. What's wrong here? What is it? No. So what? C+1 here. I can just use C. No need to use C capital. I can use small c. Uh-huh. Uh-huh. And here we can just write a function which finds uns. We can just copy it from here. Okay, it'd be great. And here we just have a static solver of size 1 million. And we here just return solver dot findance c. So now we only do it once, but in the beginning it will run for a long time. For example, I don't think it will run fast here for 1 million because I have debug configuration. To fix this, I need to go to the release version and hope that this time it will be fast. Yes, this is now fast. Okay, we can try to submit it again. Let's go to the status, and again, a minute of waiting, sitting and waiting. Is it really working? So I can put 1 million here. Yes, kind of nice. And only 3 pyramids for 1 million. For 1 million and near numbers. Wrong answer this time. Okay, as I said, I have an idea. Yeah, I have an idea. So again, let's do it. V3. V3 here. V3 here. V3 here. V3 here. Let's think what could go wrong. Yeah. So for each number, we store the minimum number of pyramids in which this is achievable. This is kind of bad. See what? This is the problem. So suppose. So suppose, for example, that this is some number, and you used some pyramid to go here. You see, now the problem is that maybe after some long time, some bigger pyramid was used here, and it rewrote everything. I wouldn't think this is something bad, yeah, because before that, this bigger pyramid P capital would rewrite this thing, and only after that it would rewrite this thing. But maybe I'm wrong. Maybe I'm wrong and I don't understand anything. Yeah, so what I want to state is that at any moment, we have an optimal answer for the prefix of our pyramids. We need to prove that for next pyramid, this is also true. So we see some number, and we want to replace it with, so we want to add this new pyramid. Ah, I got it. Maybe I got it. You see, sometimes, yeah, sometimes there is an answer for this pyramid. E. And it improves the answer for this pyramid, for the right number I. But then we also improve the answer for this pyramid, for this number I minus p dot size. And then during the restoring the answer, it will think that we need to use the same pyramid twice. Let's stress that. We need to stress that. So v3 here. I don't want it like this, so let's create the second function. Just ans. Yeah, but I want now, instead of all this, to do the other thing. So this is stress compare. But now I need the stress, which is stress same. Now I go through this million. I want only to run this answer 3. Then I need to check whether ans 3 I dot, no, if size of pyramid, this should be at least size of pyramid of ans 3 I plus 1. So if this is true, if this is false, then I need to say that incorrect is true. And if incorrect, then we need to print that. Again with stress, and let's try and run it. Okay, it found something. Oh, no, what? Failed on 14. Okay, I need to start I plus 1. This was undefined behavior. Again. What's wrong with you? Now it doesn't do. Ah, what? Wait, what? What if I print 1? Okay, it never happens. So my answer is always stress same. Wait, what? I think let's try J because I'm afraid this would spoil it. Let's print it here that everything is fine. Mm-hmm. Maybe like this. Okay, it failed actually. So now we see that there are two pyramids of the same size, 7L and 7L. The correct way of doing it is check if it is smaller or if ans 3j equals ans 3j plus 1. Yeah, so 7L and 7L. Okay, as I said, this happened because of this issue, which we need to address. One possible way would be to not store this thing. So ideally, we need to store this separately for each x. For example, we want to check if the answer is possible within x pyramids. Okay? Then we look only on the ways here of x minus 1 pyramids, of using x minus 1 pyramids. If we do so, maybe this works. To do so, we will need actually vector of vectors of DP state. So the first coordinate means the number of pyramids. And in this case, actually, we do not need this thing. So we can just return to K. So what I want to do now is to fix this struct by creating a new one. So here we will use just pyramid solver. Here we just use pyramid solver. And here is vector TP state. So first of all, 0 pyramids. 0 pyramids. Okay, we can do that. To use 0 pyramids, we need 1 and vector DP state of this. Now we need to iterate. So assume, let me think. Okay, so assume great. So I guess here we already need to fix the number of maximum number of pyramids which we can use. So for example, if x is the maximum number of pyramids which we can use, then here is x plus 1. Instead of dp state, we use simply pair int bool. Now the solution needs to be fixed. Oh, here. So still we go through all these numbers from all through all pyramids, but also we go through all, how to say, numbers of pyramids. So from pyramids equals 1, pyramids at most x. Okay, since this is x, big capital X, let's choose small x. So I need to IB at least pyramid size. And I also want this thing to be expressible with x minus 1 pyramids. So I want this thing to be possible. So if it is possible, then I update VI. So, yes. I say that VI dot first VXI. We can express I as the sum of x pyramids. If the first pyramid is the pyramid dot base. And stop. I can just put this. Yeah. Nice. It's actually nice, I think. Okay, here we need to go through all x's. So we go from int x equals 0. X is at most p dot size. And if this happens, so vx current vxc dot first is not -1, then the answer is possible. And we will find it. So we say that current volume is C, and while current volume is greater than 0 and this can be eliminated, we say that ans dot push back. We need current X as well. So here we ans dot push back v current volume current X, and we subtract it. So first of all, I guess we would like to understand what orders of x should be used here. Yeah? Which orders of x should be used here? Why is it so slow? What is it doing? Ah, is it solving the test? Stress. Stress same. Ah, it's finding the answer. Ah, it's a very slow process, maybe. Okay, this is a really slow process. Maybe we can do it smaller. 10. Okay, so it should be less than x here, less than v dot size here. Oh no, it takes a lot of memory. But why? Why so much memory? Ah, I need to subtract 1 from parent x. Now it works. Stop, what? It still said... It still found an incorrect answer. It seems so. So, what's the problem? We have some optimal answer for 4. And it uses... But actually, so there is some answer for number 183. It uses 7h. And this answer does not use 7h. But after that, this answer was updated. And actually, after that, it used 7h. Which is a disaster. So, for example, it was like 5h, 4l, 3l, but then it was replaced with some answer which uses 7l. We would like to do it, but if we do it naively, we need to add one more dimension, which is the biggest pyramid. And if we add it, it will really be huge. Also, still, it is not clear why we just use 10. Why not something bigger or smaller? Why 10? So 10 is kinda the biggest possible number of pyramids in the optimal answer. I have... So first of all, let's put something like 30 and find the optimal x. So to do it, okay, if we are doing it fairly, I need to make a pyramid solver v4. Pyramid solver v4, and here also pyramid solver v4 and v4. So let's fix our current pyramid solver, which we have plenty of. So first of all, let's put like 50 here, and we need to like validate. So let's go through all numbers from 0 to v dot front dot size, which is just c+1. And then we go through axis. And if the answer is possible, so if vxi dot first is not -1, then break. And then we want to find some maximum x. Here we say that x is maximum of x and x, but only if x is not v dot size. And after that, I want to print the result of validation. Let's print it. And we want to look at it, so we actually run the validation here. Thank you, my camera. This is really working for so long. Okay, it stopped. Maximum needed x is 6. Ah, it was so slow because of many tests here. This was stupid. But now we understand that we do not need anything more than 6 here. Let's put 6 here and let's remove the validation. What it says, so let's look into this code. What does it do? For each number I, we check the minimum x for which answer is possible. And if answer is possible, it breaks. So we see here that for every number, this x was not more than 6. So it stops at 6 or less. This means that capital X, which is passed here, should not be greater than 6 because we won't get more optimal answers with it. Also, we need to fix the find answer procedure. For that, I would like to store this vector of pyramids. So actually, this will be here. This will be a vector in the solver. Why? Because we will use it here. How will we use it? So I know for some position P, I know that I can get to home in X steps. We are asking ourselves, which pyramid should we use? Yeah? So we store some pyramid here, which can be used. But the problem with this approach is that we cannot really use. So we can use this pyramid, but after that, sometimes this says to use the same pyramid P. This is the problem. Sometimes it says just to use the same pyramid P. And this is really sad, because we cannot do it. So in order to fix that, we would like to somehow else find the optimal pyramid here. I cannot think of anything but some branch cutting. So assume that we found this vertex for which we know the optimal answer. Let's just make a brute force with backtracking. So we go. So the first step is obvious. We just use the thing which is stored in this array. But after that, we need to be careful. So if this thing is less than this thing, we do the same. But what if it is greater than the last thing? Then I think we need to go through all pyramids, which is less than this one. And check whether the answer is possible after subtracting this pyramid. I guess this will not be a huge mess, but it's kind of disappointing. I wouldn't like this problem to be solved like branch cutting, something like this. Okay, let's try and do it. Okay, so we go here. We have some answer. We have this. And what we do is we write some function which is fill ans at most. What is it? We need to fill the volume, current volume. Okay, the volume C, let's just do it. With X pyramids. And with maximum pyramid, which is less than the mth pyramid from this vector. And what is a pyramid? Pyramid is pair of size and its space. Okay. So I want to use mth pyramid. Here, actually, I can store the number of this pyramid. So let's put int here, which still can be -1. Yeah, but this time instead of here it's 0 or whatever. Now we go through pyramid indices. Go through this, and if I is at least pyramid size, yeah, we need pyramid index dot size. And vx minus 1 I minus same thing. Then we store here not the pyramid itself, but its index, which is pyramid index. Also, it seems that here we need to just remove first. Yeah. So validate, we don't need it now anymore. But I can fix this validate by this. So fill uns at most. I need to fill C cubes with at most with exactly X pyramids, and maximum of them should be at most mth pyramid. And I put the answer in a vector pair bool. And maybe bool. So if it was successful, then I write it here. Okay, so I create the answer of size 1 and pyramids VXC dot base. And I run this function fill at most, answer at most, which is C minus this dot size X minus 1, and the number of pyramids should be at most this minus 1. And I put it in the answer. Then I return answer. So here we need to be careful, because we don't need to repeat the same pyramid. So first of all, if C equals 0 and X equals 0, and we return true, because we are happy we have done it. So after that, let's look into let's look into the answer. So we say int. We can just look into vxc, I guess. So if this is less than is at most m, then we are fine. First, we just put it in the ans. And we print the sans. No, we don't print the sans. We continue filling like this. And we can return it, basically. So what if this is not true? This means that, sadly enough, we have to iterate. So I can also say if, let me think, vxc actually equals -1, then return false. Yeah, because this is impossible. Finally, we iterate through all possible pyramids. And we try them. Actually, so in such functions, what you need to do is, so if the function failed and returned false, then you need to make the array the same state as it was before your function. So if I were a good person, I would write here like this. So bool answer equals this. If not bool ans, then I need to ans.pop back. And only after that I return bans. So this is the correct way. The reason why I wrote it as before is because actually it cannot return false. It always returns true because of the structure of the problem. I don't need anything. But let's write it like this so you learn something from my video, which is already almost 2 hours long. Oh, goodness. So here I iterate, and I just do the same thing, actually. So I ans.pushback pyramids p. Then I try subtract its size. Also, I would like to, if x is less than 0 or c is less than 0, or at most even, then return false. Or else something will break. And here I don't need to return beyonds. Okay, actually, I just do not need to return beyonds. Never. So just I can write else return true. Or even like this. If beyonds return true, and then without branching, I just pop back. This is the most nice way. and return false if the branching failed. Okay, now it should be fast enough. Everything's fine, it says. Okay, let's check. Let's check it. How fast is it? It is acceptable, but it's not really fast. To check whether it's fast or not, we can include chrono and print something like this. So we can auto start equals chrono high resolution clock now, then auto end equals the same thing. I would like to do it in on PC because maybe it breaks something. High resolution clock.now. So this is a basic setup for measuring time. Start equals now and end equals now. And then we can print something like total elapsed time. Then we subtract end minus start. And we get a special object called duration. Some people just count nanoseconds in it, but I don't like it. Instead, I just divide it by 1 millisecond. And I print that it is in milliseconds, of course. Let's see how long did it work. You see, second and a half. Which is fine because we have 3 seconds here. Okay, maybe it will work this time. And if not, then I don't know. I really don't get it why people solve it so massively. This is not really a nice problem. This is a bit painful because of this condition of the sizes being different. Yeah, this is painful. I think it will be a compile error because it doesn't even know what is chrono, what chrono is. Time limit exceeded. So could I do better? I don't know. I don't know if I could do better. Actually, does it run all these functions? Like v1, v2, dp solver v3, dp solver v4. Does it do it? No, I think no. I think it doesn't do it. still the solution is too slow for some reason. This is fine if this is because of this strange function. I need also to do this. So if it is already there, yeah. Why is it slow? It should be fast. It really should be fast because I guess it cuts everything slow. Let's try stress measure something. So we like run find dance of 0. Then we go through all numbers. And we find the maximum duration. So we say that d equals maximum of d and n minus. So if n minus start is greater than d, we print say new maximum d milliseconds. And let's make some side effect, or else it will optimize out. To get answer once 3 dot size at least. And I want stress measure. Okay, it's blazingly fast. It's really fast. So the problem is with my... What's the problem with my solution actually? Maybe I can swap my 2 dimensions. So instead of C and X, I can use X and C. Will it improve it? I don't know. But maybe... I really don't know. Maybe it's worth a try. First thing that I want to do is to try Pragma. Pragma, GCC, optimize. O3 and unroll loops. Maybe this will help. No, the thing that will help is to actually print ans and not. This is fine because this is inside on PC, and everything is fine. How doesn't it fit into 3 seconds? My solution is not that slow. And my computer is not that fast. Well, it is fast, but because of several cores of CPU. Maybe it will be again tail. Compile error. Oh, why did I wait for this? This compiler is ugly. Okay, I guess we will cover it with on PC. So this works in 1.5 seconds, or maybe 1300, 1400 milliseconds. Let's now try and optimize it. By swapping the dimensions. So this is like v5. This is v5. This is v5. And this is v5. Now instead of all of that, I try to swap the dimensions. So here I have c plus 1, and here I have x plus 1. And now everywhere I need to swap their dimensions. Op, 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 op. Op, op. Op, op, op. Op. Op, op. Op, 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 op. Wrong answer. So now this is wrong answer. Now I really don't know what can fix this. Also, we need to swap this and this. Okay, let's try it now. It is much slower. Okay, never mind. This was a really bad idea. Okay, we can use it as v6. But now we actually want v5. So let's try and prove that if at some moment we say that vxi equals p, this means that there is an answer which gets to C in X pyramids, and the maximum of these pyramids is P, and these pyramids are different. We will prove this by induction and assume that at some moment this is true. Then at some other moment we find new answer, Vxc, which is equal to P. What does it mean? It means that V x minus 1 C minus P dot size is not minus 1. This means that this state is accessible through the smaller pyramids. Smaller because for the pyramid P, we iterate C's in decreasing order. Yeah? So this means that this answer is accessible without big pyramids. And it should be accessible. Fine. Okay, what to do then? There are two ways. First of all, we can find the error, or we can rewrite it a bit. I think both are fine. I need to understand what is easier in this situation. As you may notice, I am not really fresh now. Is it false? I really don't understand why this solution should be wrong. Okay, there are a lot of failures actually. And the minimum one is 227. Let's see. What is 6H? $91. Can we do it in debug and see what's wrong? So slow. Okay. Let's look at X and C. And for some reason, V0, C, and V1C, and V2C were minus ones, but 5C was actually non-zero. And after that, it failed to fill this number. So let's look at VXC. It says that it is 9. Let's look at pyramids VXC. It is of size 91, so we need to subtract them. Now get the residual thing with 136 and 4 pyramids. Yeah. And the maximum pyramid should be at most 8. But sadly enough, VXC was also 91. Yeah. It was again 9. So instead of that, I guess we tried all the pyramids here. And I guess all of them failed. Let's think, for some reason, we said that V5 227 is 9. Why did we do that? We did that because it kind of was the only way. And it meant that V4 136 at that moment wasn't minus 1. Maybe it wasn't 9, like here. But it wasn't -1. So I guess this means that there is a possibility. Pyramids 320. So starting with, there are not that many. Okay, let's try something. I want to try V3 136 minus pyramids 0 dot size. Okay, this is 9. What about 8 or 7? Oh, for example, 7. But now the same trick. It wants it wants to use the 7th pyramid for some reason. Okay, let's see. $80. So V380 is 7. But can we do 80 without 56? Actually, of course we can. Yeah, for example, 55, 20, and 5. Yeah, no problem. So why did it fail? So I am assuming, I am stating that we need pyramid 7, pyramid 9, 7, 6, 3, 0. Okay, here we go. Now I am assuming that we are fine with 6. It didn't work. Ah, I should start with M here, of course. Oh, this was so stupid. Why did I make this stupid bug? Dude, why are you so slow? Now it works. What about a lot of fails? No fails. Okay, maybe this will work this time with these unroll loops and O3. However, I don't like it that it requires pragmas. It's not good. Actually, it is near. It's it's funny. See, it's only C++11, and it's kinda authentic because in 2011 there was no C++14 actually, or at least I think so. So maybe it is just really close to the format of that finals. This is why we do not get C++14 or 17, only 11. What if I write ICPC finals like 2006? I will not get STL at all. This would be crazy, I guess. Well, it's all funny, but I really wanted to. Oh, finally. If it weren't accepted, I really wouldn't know what to do. This is exhausting, guys. Such an easy problem. You see, 134 teams solved it. And I again spent 2.5 hours to solve this single problem. And I didn't like pushed on brakes for purpose. I didn't slow myself down. I really wanted to solve it as fast as possible, but with some explanations. And still, it took 2.5 hours. Dudes, in 2011, people were actually crazy. I don't know how to explain it. I legitimately don't know how these people solve this problem. They should not be normal. I don't want this to be normalized. I don't want this to be normalized. As far as I know, top one on the on-site was Zhejiang University. So congratulations to them for this nice contest with problem J. I think I might just abandon problem J forever. So if I open a sub-contest and see a problem J there, I don't solve it. I give it to my teammate, I put it in trash bin, but I don't solve it because, God, this was not good. This wasn't good.